for the
Yeah.
Go on.
Sorry, I just have to click to the got it. Oh, la, la. Okay. Play. Okay. Yeah. And so I will describe the method that we use in order to measure this distortion of time with future survey. Okay, so to understand how the distortion of time contributes to our observable, we first need to understand what we are really measuring, what is our observation. So when I will concentrate here on the clustering of galaxies. So when we receive a map of galaxy like this one from SDSS, what we usually do is to pixelize these maps. So to split it in bins of solid angle and redshift, and then to count how many galaxies we have in each of these pixels. And we are interested actually in the fluctuation in the number of galaxies from pixel to pixel. So we can construct the observable, which I call here capital delta, which is simply the number of galaxies in a given pixel minus the average number and divided by the average number. And so the question is, what is the theoretical modeling for this quantity delta that we can directly measure? So in our first approximation, we would be tempted to say, okay, galaxies follow the distribution of dark matter, and therefore the fluctuation in the number of galaxies is directly related to the fluctuation in the distribution of dark matter. And there is this bias B which relates the two quantities. However, we know that this is just an approximation and that in reality there are some distortions that also contribute to this observable delta. And these distortions come from the fact that we are never able to observe directly the position of galaxy. What we are able to observe is the redshift of the galaxy. So we measure the shift in the spectrum of the galaxy. And we are also able to measure the direction of the incoming photon, which I call here N. Now, if our universe would be perfectly homogeneous between the galaxy that we observe and us, we could actually directly infer the position of the galaxy from a measurement of redshift and N, because in a homogeneous universe, once we know the redshift, we can calculate the distance. Of course, we need for that a background cosmology, but once we have it, we have a direct relation between the two. And also in a homogeneous universe, light propagates on straight lines. So it means that if we know the direction of the incoming photons, we know directly where the galaxy is. Of course, we know that we don't live in a universe which is perfectly homogeneous, and this has an impact because it means that the photons will travel on perturbed geodesic, and this will actually modify the relation first between the redshift and the distance. This relation will be affected by the inhomogeneities in the universe. And second, we have also a change in the direction of the photons along the trajectory. And so this changed the angular position of the image. So this means that when we look at a map of galaxy, like the one from SDSS, the structure that we see on this map, they do not reflect directly the underlying distribution of the dark matter, simply because the position of the galaxies have been shifted radially and transversally with respect to the true position in the sky. The observed position is shifted. And so, of course, this will modify the observed distribution of galaxy in the sky, so our observable delta. So if we want to really describe what we are observing, we need to account for this distortion in the description of the observable delta. Now, it is possible to do that in a completely consistent way to account for all these distortions. For that, we need, of course, a model for the geometry of the universe. So in the following, I will use the following metric, which is a perturbed Friedman metric. So A is the scale factor that describes the expansion of the universe, and psi and phi are the two gravitational potentials that describe perturbation in the spatial component of the geometry and in the temporal component of the geometry. So in such a metric, we can calculate the propagation of light. So here I'm interested in what happens at large scale. So I assume that these gravitational potentials are small, which is the case at that large scale. And then at linear order in perturbation theory, we can calculate the propagation of light, calculate the relation between distance and redshift, between the incoming and direction at emission. And putting everything together, we find this expression here for the observable delta. So the first term in the first line was our naive guess, saying that the distribution of galaxies follow the distribution of dark matter. And all the other terms are distortion coming from the propagation of light in an inhomogeneous universe. So in the first line, we have here this effect, which is the well-known redshift space distortion. So it depends on the peculiar velocity of the galaxy projected along the direction of observation. So the peculiar velocity is the velocity that the galaxy have in addition to the Hubble flow. Then we have in the second line the effect of gravitational lensing, which changes the focusing of light, and therefore it changes the solid angle in which we detect the galaxy. So it changes the number of galaxies that we see per unit of solid angle. And then the last three lines here are what has been called in the literature relativistic effects. So these relativistic effects that depend also on the peculiar velocity of the galaxy, but in addition, they also depend on the two metric potentials phi and psi separately. So these expressions really describe what we are observing in the linear regime, all the terms that contribute to our observation. However, at the moment, this is not the expression that is used to analyze current data. What people are using for current survey is the first line, the sum of density perturbation and redshift space distortion. And all the other terms are neglected, and they are neglected for a good reason, which is that they are strongly subdominant for current survey in the regime probed by current survey. But we will have a lot of future surveys that are already under construction or planned for the next few years, like Euclid, DAISY, the Square Kilometre Array. And with these other surveys, these other terms will become important. So gravitational lensing will become important at high redshift, and relativistic effect will become important when we have large volume of observation. And so the question that we can ask ourselves is, how can we use this expression, this delta, to test the theory of gravity? And also, are these relativistic effects that are subdominant with respect to density and redshift space distortion, are they useful to test gravity? Can we learn something more by having this relativistic effect into the game? So what I will show you in this talk is that, yes, the relativistic effects are actually very useful. And in particular, there is one effect which is crucial if we want to test gravity in a model-independent way, which is this term here, which contains the distortion of time. So to understand how we test gravity and why this effect is useful, we need to describe a little bit what we mean by testing gravity. So what we want to do is to test gravity at late time, so during the stage of the accelerated expansion of the universe, where we can observe galaxies, so between redshift 0 and let's say 3. And so over this redshift range, our universe can very well be described by 4 fields. So first we have 2 fields that describe the perturbation in the content of the universe, so delta is the density fluctuation, and V is the peculiar velocity of galaxy. And then we have the 2 gravitational potentials that describe perturbation in the geometry of the universe. And so when we want to test gravity, we want to test the relation between these 4 fields. So in general relativity, we have specific relation between the fields. We have, for example, the Poisson equation, which tells us how the matter perturbation distort the spatial geometry of the universe. We have the continuity equation, which tells us how a flow of particles can change the distribution of the matter. We have the Euler equation, which tells us how matter falls into a gravitational potential psi. And in general relativity at late time, we can actually show that the 2 metric potential, the 2 gravitational potential, phi and psi, are actually the same. So this is valid in general relativity, but when we modify the theory of gravity, very generically, we modify the relation between these fields. And so ideally, what we would like to do is to measure the 4 fields separately, and then to test the relation between them to see if it's compatible or not with general relativity. Now, the problem is that currently we are not able to do that. And the reason is very simple. It's because currently we have only 3 independent measurements of these 4 different quantities. What we are able to measure at the moment is the density and the peculiar velocity from redshift space distortion, from distribution of galaxies, and I will describe that in a bit more detail in a moment. And in addition to that, at the moment, we have a measurement of the sum of the two gravitational potential, phi plus psi, via gravitational lensing, that we can measure either by looking at the magnification of quasars, or by looking at the cosmic shear, or by looking at the CMB lensing. In all these cases, what we measure is phi plus psi integrated along the trajectory. And so these limit our ability to test gravity, because we cannot test 4 relations with only 3 independent measurements. And this actually has an important impact on the type of test of gravity that we are able to do. So let me be a bit more specific here and discuss a specific case where we would like to distinguish between a modification of gravity, where we change the laws of gravity, and a universe where we would have a non-standard dark matter that would be affected by an additional force, a force that can be non-gravitational and that would act only on dark matter. This is what I call a dark fifth force. So these two types of scenario, they will both change the way the structure are growing as a function of time. And the question is, can we distinguish between these two types of deviation from lambda CDM cosmology? So to understand if we can distinguish between these two examples, let us first look at the equation that governs these two models. So when we modify the theory of gravity, we modify the relation between the fields. And so usually we can generically encode this modification independently on the model into two free functions, eta and mu. So eta is a function that modifies the relation between phi and psi. It's equal to 1 in general relativity. It's generically different from 1 if we modify the law of gravity. And then we have this function mu, which modifies the Poisson equation, the link between the metric and the density. And so when we modify the theory of gravity, if we work in the Jordan frame, then we don't modify the Euler equation. We don't modify the way the matter falls into a gravitational potential, because we can work in the Jordan frame where all the modifications are encoded into the change in the Einstein equation. On the other hand, if we have an additional force acting on dark matter, but we don't modify gravity, then we have the standard equation in general relativity. But of course, we will modify Euler equation because we have an additional force that acts on dark matter. And we can show that very generically for very different types of model with a dark force. We can encode that into two functions, these theta and gamma. So gamma is really an additional force acting on dark matter, and theta is a friction term that acts on the motion of the dark matter particle. So this is at the level of the equation. Now what we want to understand is how these two models impact the way structures are growing as a function of time. So we can combine this equation to obtain an evolution equation for the density. In the case of modified gravity, what we see is that the growth of the density is directly affected by the function mu, by the change in the Poisson equation. Whereas in the case of a dark fifth force, we see that the growth of structure is affected both by the fifth force and by the friction term. And so if we compare these two equations, we see that they are very similar. In both cases, we have an effective Newtonian constant, which replaces the standard G. In the case of modified gravity, G is just multiplied by this mu, whereas in the case of a dark fifth force, we have the impact of the fifth force on this Newton constant. And so there is a small difference, which comes from the fact that in modified gravity, all matter is affected by this modification, whereas in the case of a dark fifth force, only the dark matter is affected. And this is reflected in this parameter x that I have in front of gamma, which is the fraction of dark matter that we have in the universe.
So we have a question.
Yeah. So do you want me to mute?
Hello? Okay. Hi, Camille. I have a simple question. Are these parameters, eta, mu, and gamma, theta, are they k-dependent, or do they depend on something, or just constants?
So In general, they depend on redshift, so they evolve with the redshift, and they also depend on scale. In the following, I will actually neglect the scale dependence because in the quasi-static approximation, we can show that in many, many models of modified gravity, the K dependent is subdominant. But if you want to be completely general, they should depend on both time and K. Okay.
Thank you.
Okay, thanks. Okay, so yeah, so if we look at this two type of equation, then we see that the impact on the growth of structure will be very similar, because since we don't know the strength of the fifth force, the fact that it is multiplied by the fraction of dark matter is not enough to help us to distinguish between the two types of scenario. In the case of the dark fifth force, we see that we have also this friction term, but actually in many models of modified gravity, of dark fifth force, this term is subdominant, it is negligible. And even if it is not negligible, it is itself degenerated with the fifth force. So having this term is not helpful to distinguish between the two types of scenario. So from that, we see that in both cases, we have an enhance in the growth of structure. And so we cannot distinguish the two types of scenario with redshift space distortion. And this is something that is actually well known. If we have a fifth force or if we modify gravity, in both cases, we change the way structure are growing, and it's very difficult. I mean, it's impossible to distinguish between the two. But so what people have realized is that even if there is degeneracy at the level of the growth of structure, if we look at the equation, we see that we have a clear difference, which is the fact that in modified gravity, the two metric potentials are different, whereas in the case of a dark fifth force, they are the same. And so the proposition was to measure this anisotropic stress, the relation between the two, and from that, to distinguish between these two types of scenario. In particular, if we would measure an eta different from one, this would be a smoking gun for modified gravity. However, if we look in detail at how the measurements are made, we see that we cannot use this test at the moment. We are not able to do it properly. And this really comes from the fact that we have only 3 measurements of the 4 quantities. So the tests that people have performed are the following. They have measured the gravitational lensing, which is a measurement of phi plus psi. And then via redshift space distortion, they measure the peculiar velocity of the galaxy. They use Euler equation to infer psi, the time distortion, from the velocity. And then they compare the two to see if phi is equal to psi or if they are different. So if we are in the case of a modification of gravity, the procedure is perfectly correct. We can really infer psi from Euler equation. We can compare the two, and we can say if we are in modified gravity or not. But if we have a dark fifth force in our universe, the procedure doesn't work anymore because Euler equation is not valid anymore. So when we use Euler equation to infer psi, we're actually not able to infer psi. What we measure is really this psi effective, which is psi multiplied by the fifth force. This is the quantity that we can extract from our data. And then you see that if we compare phi plus psi with this psi effective, we will see a difference, not because the two potentials are different, but because we have inferred a wrong potential from the velocity that we have measured. So it means that in the 2 cases, we would actually see an anisotropic stress, even if in the case of dark matter fifth force, there is no anisotropic stress. So we cannot use an eta different from one as a smoking gun for modified gravity. It's not correct with current data. And so let me maybe here rephrase the argument in terms of this mu sigma parametrization that you may be familiar with, which is the one that is used by current lensing and redshift space distortion survey. So this parametrization comes from the combination of the Poisson equation and the anisotropic stress, which allows us to write the sum of the 2 metric potential in terms of the density, and the relation between the two is governed by this capital sigma, which is just 1/2 mu 1 plus eta. And so the way people have done the constraints so far is the following. So here you see a plot by the DES collaboration, the most recent measurement of modified gravity. And so what they do is the following. They combine redshift space distortion with gravitational lensing. So from redshift space distortion, they obtain this green region, this green constraint. So redshift space distortion is sensitive to mu via the growth of structure, but it's not sensitive at all to sigma. And then with gravitational lensing, they obtain the blue region. So gravitational lensing is sensitive to sigma via the equation above, and also very slightly to mu because it depends also on the growth of structure on delta. And so by combining the two, you see that we obtain strong constraint on mu and sigma, which is the purple region here. And so if one measures mu and sigma, we can then measure eta. Now, this procedure, as I said, is perfectly valid if we want to test modified gravity, but we cannot test a dark fifth force with this procedure, because what happens is the following. Suppose that we have an additional fifth force, but that gravity is general relativity. Then with this type of constraint, we would measure sigma, the true sigma, via gravitational lensing, which is equal to 1 if we are in general relativity. So here sigma 0 is the deviation from 1 today, so that's why it's centered at 0. But then with redshift space distortion, what you measure is not the true mu, it's not the change in the Poisson equation, but it's the change in the growth of structure, which, if we have a dark fifth force, is affected by the fifth force. And so when you combine mu effective with sigma, which depends on the true mu, there is, of course, an inconsistency between the two. It's not the same mu that enters into the two parameters, and this would lead us to find an eta, which is different from 1, even if we don't have a modification of gravity. So we see that with current survey, we are limited in the possibility to distinguish between these two types of scenarios that are at the fundamental level completely different. And here is why relativistic effects are interesting, is because they provide us with a direct measurement of the distortion of time with this effect here. And what is interesting is that here we really measure the true psi, because we are sensitive to the way photons escape a gravitational potential, which is sensitive to the true psi, even if we have a dark fifth force. So independently on the model that we have in our universe, we are able to measure the true psi with the relativistic effect. Now, of course, in order to be able to do that, we need a way to isolate this effect from the rest, because when we measure the clustering of galaxies, we are sensitive to the sum of all these terms. So if we want to use one of the terms to test gravity, we need a way to isolate this term. And luckily, we can do that by looking at the correlation function and looking at the fact that the correlation function has different features depending on the different terms we are looking at. So once we have a map of galaxy like this one, what we usually do is to correlate pixels. So we measure the correlation of delta in different pixels, and then we average over all the pixels that we have in the sky. If there would be only the density contribution in delta, the correlation function would be very simple because it would be completely isotropic. So it would depend only on the separation between the galaxy, which I call D, but not on the orientation of the pair. Adding redshift space distortion, it is well known that we break this isotropy of the correlation function, because redshift space distortion can change the apparent redshift separation between the galaxy, but it has no impact on the angular separation between the galaxies. And so because of this term, the correlation function depends not only on the separation, but also on this angle beta that describes the angle between the pair of pixels that we are looking at and the direction of observation. And so it's possible to calculate the specific dependence of the correlation function on beta. It has been done by Kaiser and Hamilton in the 90s already. And what they found is that in addition to an isotropic part, we have specific modulation in beta. We have actually a quadrupole, which depends on the Legendre polynomial of degree 2 of beta, so basically a cos square. And we have also an hexadecapole. And this is very interesting because it provides us with a way of separating density from peculiar velocity. So what we need to do is simply to do 3 types of correlations. First, we can correlate delta-delta average over all pixels. By doing that, we would actually just measure the isotropic part and we get rid of the other part. Then we can measure delta delta and weight by a cos square, by the Legendre polynomial of degree 2. By doing that, we extract the quadrupole. And finally, we can also extract the hexadecapole. So we have 3 different measurements. And then we can combine these different measurements that depend differently on density and peculiar velocity to actually measure separately density and velocity. So this is what has been done with a lot of success by redshift survey like SDSS, BOSS, WiggleZ, and eBOSS. This is the way to measure the velocity and therefore the growth rate of structure. Now let us look at the relativistic effect. So the relativistic effect, they are very interesting because they break the symmetry of the correlation function, which is a different thing than what redshift space distortion does. So what I mean by breaking the symmetry of the correlation function is that because of the relativistic effect, the correlation function is not the same if I look at a galaxy which is behind my central pixel or a galaxy which is in front of the central pixel. Now, of course, you understand immediately that if we want to measure such a breaking of symmetry, we need more than just one population of galaxy, because if all the pixels are the same, what is in front and what is behind is actually ambiguous. So we erase by construction any asymmetry in the distribution of galaxies. But what we can always do is to take our population of galaxy and to split that into a bright population and a faint population. And then we correlate the bright with the faint. And because of the relativistic effect, we have a difference in the amplitude of the correlation function when the faint galaxies are behind the bright one or in front of the bright one. Now, see, this may seem a bit strange, but we can develop an intuition about why this is happening with relativistic effect by looking at this very simple situation here. So suppose that we have an observer sitting at O, and he looks at 3 galaxies, one behind the other. In the middle, there is a bright galaxy, and in front and behind, there are 2 faint galaxies. Now, suppose that the bright galaxy sits at the bottom of a gravitational potential. This is actually what will happen in average, because the brightest objects, they tend to be at the center of big cluster of big large-scale structure. So if we look at the light emitted by the bright galaxy, it has to climb from the bottom up to the observer. And by doing that, the photons lose energy. And so the redshift of this galaxy is shifted to the red. The galaxy appears slightly further away than it is in reality. Then if we look at the faint galaxy, which is in front, the faint galaxy is not exactly at the bottom of the potential, it's a bit higher up. So the light also has to climb out of the potential to reach the observer, but the climb is a bit smaller. So it means that this galaxy is also shifted to the red. It also appears a bit further away, but the shift is smaller than the one experienced by the bright galaxy. And then if I look at the faint galaxy behind F1, you will see I have chosen here by construction a situation which is symmetric, and therefore the redshift of F1 is exactly the same as the redshift of F2. So now if I look at the separation between bright and faint, I see that D1, the separation between F1 and B, is now smaller than D2, the separation between B and F2. And because the correlation function depends on the separation between the galaxy, this means that systematically, a faint galaxy which is behind a bright one will be more strongly correlated with the bright one than a faint galaxy which is in front. Now, of course, this is a very idealistic situation. In reality, we don't have all bright galaxies sitting exactly at the center of a gravitational potential, but actually the idea is the correct one. So we showed that if we average over all possible pairs of bright and faint galaxy without making any assumption about where they sit, what we find is really a dipolar modulation in the amplitude of the faint galaxy around the bright one. So we find this correlation function which has a given amplitude and a modulation that goes like cos beta. And so this is very interesting because it gives us now a way of targeting this relativistic effect. What we need to do is simply to split the population into 2, to multiply bright with faint galaxy, then to multiply this by the cos beta. And by doing that, we directly extract the amplitude of the dipole, and we get rid of density and redshift space distortion that generates only even multiples in the correlation function. So this really gives us a way of targeting the effect that we want. So if we go back to the expression that I showed you for delta, we can show that by looking for a dipole, we get rid of all the terms that I have crossed here in blue, and we actually isolate not only gravitational redshift, which is the last term in the red region, but we are also sensitive to Doppler terms, to the peculiar velocity of galaxies. But this is not a problem per se, because we know that we can measure the velocity of galaxy via redshift space distortion. So we simply need to combine the dipole with the even multiples to target the gravitational redshift. Okay, so let me discuss a little bit how we can do that in practice, how we can combine these different multiples to measure directly psi. So what we do is first to define transfer function. So we relate the density at a redshift z to the primordial potential generated by inflation via a transfer function. And so we do that for the density, the velocity, for psi, and also for phi plus psi that we can measure with lensing. And then we are interested at the evolution of this transfer function at late time. So by late time, it's when all modes of interest are already well inside the horizon, and we are dominated by dark matter and by matter and by dark energy. So radiation is negligible. So in this regime, if we are in general relativity, the growth function d1, which describes the evolution of the density, is simply a function of redshift. On the other hand, in general, if we have modified gravity, the growth can depend also on scale. So we replace it by a function d1, which depends on k and z, and which is completely generic, that we want to measure with our data. And here and in the following, we will actually do one assumption to simplify the calculation, which is to choose this reference redshift z star with respect to which we describe the evolution of the perturbation before acceleration has started. And we assume that at this point, we recover a standard cold dark matter universe with general relativity. So we link every deviation from lambda CDM to the onset of acceleration, to the fact that we have a strange behavior in our universe at late time. This is, of course, an assumption and a restriction about all the different types of model. It's not essential to the formalism. It just simplifies a little bit the calculation, and that's why we decided to use that in our forecast. So this is for the density. Then we can look at the velocity. So in general relativity, the velocity evolves in this way. So it evolves with the function f, which is the growth rate, which is simply the time, the derivative of the growth of the density. But if we want to be completely generic, we replace this growth rate by a function g, which simply encodes the evolution of the velocity. And again, that we want to measure with the data. We don't make any assumption about g. Then we can do the same for psi, for the time distortion. So in general relativity, the evolution of psi is directly linked to the evolution of the density. You see that it evolves like omega matter times d1. But of course, if we are in different theories of gravity, we change Poisson equation, we change the link between phi and psi, and therefore the evolution may be different. So we encode that into this function I. And similarly for phi plus psi, in general relativity, they also follow the evolution of the density, but in a modified theory of gravity, they will evolve with a free function that we call J. And so we have 4 functions that encode the evolution of all the fields. So the density, d1, the velocity, g, the time component of the metric, I, and the sum of the 2, j. And so the question now is, how do our observable depend on these 3 functions? So first we can look at the even multiples, so the standard redshift space distortion analysis. And we see that we can write these 3 multiples in the following way. So we have actually 2 types of ingredients. We have this function mu0, mu2, and mu4 that are evaluated at the redshift z star, so before acceleration started, and that depends simply on the matter power spectrum at this redshift z star. And so this quantity can be constrained by the CMB. It's really early universe physics in the sense that it does not depend on what happens when we have acceleration. And so it's something that we can either keep fixed, directly constrained by the CMB, or in a more general analysis, we would actually combine large-scale structure with CMB, and the CMB would determine this function. And then we have quantity at late time. So we have this B hat and J hat. So B hat is the product of B and sigma 8, the growth of the amplitude of the power spectrum. And J hat is J times this combination sigma 8 over D1. And so what these even multiples tells us is that we are able, by measuring these different multiples, we are able to measure B hat and J hat in each of the redshift bin where we are doing our observation. And so if the continuity equation is valid, J hat reduces to F sigma 8, which is the quantity that is standardly measured in large-scale structure survey. So this is for the standard term. Now, if we add the dipole that is sensitive to the time distortion, so the dipole can be written in this way. It depends again on G hat, which has already been constrained by the even multiples. It depends, of course, on the bias. And this time we have two different biases, the one of the faint population and the one of the bright population. And then what is interesting for us, it depends on this function I hat, which encode the evolution of psi. So it means that if we combine the even multiple with the dipole, we can measure the biases, the function G, and this function I in a fully model independent way. So we measure that redshift bin by redshift bin without having to make any assumption about the theory of gravity. We really use the data to measure the evolution of the potential. Just one remark here, which is that I have dropped the dependence in K. So I have assumed now that this function depends only on redshift. This is to simplify the analysis, and also, as I said, because in many models of modified gravity, in the regime where we can measure this function are well approximated by independent function of K. But in general, we could also complicate the analysis, make it more general by allowing for dependence in K. It's not something which is impossible. Okay, so with my PhD student, we did some forecast on how well we can measure the evolution of psi, so this function I hat, from a survey like the square kilometer array in this second stage of observation. And so you see here the constraint redshift bin by redshift bin. And so at low redshift, we are able to constrain this quantity between 20 and 30%. And then if we go to higher redshift, we actually lose constraining power, which is mainly due to the fact that we have less galaxy at high redshift. And so the shot noise kills the constraint. So then if we want to measure the anisotropic stress, in addition to measuring the evolution of psi, we need also to measure the evolution of phi plus psi in order to be able to compare the two quantity. And this we can do by looking at what we call galaxy-galaxy lensing. So the correlation of cosmic shear at high redshift with clustering at low redshift, we can easily show that this correlation is sensitive to phi plus psi at the position of the lenses. And here I show you below the angular power spectrum for this type of correlation. And so you see that it depends directly on this function J, which encodes the evolution of phi plus psi. Now, this J is fully degenerated with the bias. And so if we add to this measurement a measurement of the clustering of the lenses, we can break the degeneracy between the two. And so we did some forecast on how well we can measure this function with a survey like LSST. And so here you see that we have constraints that are extremely good at the level of a few percent. And so once we have these two measurements of J and I, we can actually take the ratio between the two. And this ratio is directly proportional to eta, to the anisotropic stress. And so here you see the forecast that we have on the measurement of eta. And so we can expect to constrain eta at the level of 20 to 30% at low redshift. So the error is mainly due to the difficulty in measuring the dipole. And so this method really restores eta as a smoking gun for modified gravity. If with this method we find an eta which is different from 1, then we can say for sure it is due to modified gravity. It cannot be due to a dark force acting on dark matter. It's really a modification in Einstein equation that modifies the relation between phi and psi. Okay, so in the last few minutes, let me describe another project which is related to that, which is how we can test Euler equation. So until now, I showed you that with the dipole, we can measure the anisotropic stress, but actually with the dipole, we can also test directly the validity of the Euler equation, since we have this direct measurement of psi. So here I take the expression that we have for a generic Euler equation that has been modified by these two parameters, theta and gamma. And so the question is, how well can we measure theta and gamma by combining the dipole that measure psi with the even multiple that measure the velocity? And as before, the question is, can we distinguish this modification in Euler equation from a modification in Poisson equation? And so to be able to see if we can distinguish between the two scenarios, what we did is to put the two scenarios together and to see if we can distinguish, if we can measure separately the different parameters. If we cannot, then it means that the two scenarios are indistinguishable. If we can, then it means that we can link any deviation that we see to one or to the other. So we took this evolution equation, which depends on theta, gamma, and mu. We assumed something which is usually assumed in the literature, which is that this function, they evolve proportionally to the amount of dark energy that we have in the universe. Again, this is an assumption. It's not mandatory to do it, but we wanted to reproduce what people were doing in the literature. So we chose this evolution. And then we did some forecast on how well we can measure this quantity. And so first, with the square kilometer array, if we have just even multiples, so standard analysis, you see that there are complete degeneracy. So first, there is no way to measure separately mu and gamma. They are fully degenerated. The only quantity that we can measure is the sum of the two. And then we have a strong degeneracy between mu plus gamma and the friction term theta. On the other hand, if we add the dipole, we break the degeneracy. So you see that with the dipole, we are able to measure the three parameters independently. So we are able to measure mu and gamma independently. And this really comes from the fact that we are not only sensitive to the growth of structure for which these parameters are degenerated, but we are also sensitive to the gravitational redshift, so to the way photons escape the gravitational potential. So we can really probe psi, compare with V, and with that we can test the validity of the Euler equation, and therefore we can measure different parameters independently. Okay, so let me conclude by briefly summarizing what I've said in this talk. So I hope I convinced you that relativistic effects in galaxy clustering are very useful to test gravity in a model-independent way, and in particular, gravitational redshift, which is one of the relativistic effect, the distortion of time, is essential if we want to distinguish modified gravity from a dark fifth force. And to isolate this effect, we need to look for a dipole in the cross-correlation function of bright and faint galaxy. And I showed you two types of tests that we can do by doing that. The first one is to measure directly the anisotropic stress. And the second one is to test the validity of the weak equivalence principle. Okay, I'll stop here. Thank you.
Okay, thank you, Camille. So, wait, I have to mute here. So, thank you, Camille, for your seminar. We have some time for questions. So, if anyone has one, please go ahead. So, there's one over there.
Yeah. Hello, Camille. Ciao.
Hi.
So, okay, thank you very much. I have one question. So you said that there's a problem on well, okay, the error especially come from how difficult it is to measure the dipole, right? So that's the reason. So I think this includes also the local motion of the Earth. Is that correct?
No, so this is the dipole of a faint around a bright galaxy. And so the motion of the Earth would be subdominant in this case. The motion of the Earth would generate a dipole in the distribution of galaxy around the observer. Now, of course, it has an impact on the correlation function because the correlation function in front of the motion or behind the motion will be different, but it's an effect which is higher order in perturbation theory. And therefore, we neglect completely that we neglect that in our approximation. Assume that the velocity are small enough that we can neglect the impact of the observer velocity.
Okay, thanks. Yeah, it makes sense actually.
Any more questions? So there's one over
there. Hello. Well, first of all, thank you, Camille, for your excellent talk. I enjoyed it a lot. And I am more worried about the observational part of this thing. I was thinking that in one moment you mentioned that this modified models can be proved, for example, with large surveys like SDSS. And if it is possible to compare, for example, what difference would be in the fields measured from this large structural measurements from SDSS or past surveys, and what do you expect for future surveys, or what could be different from, for example, incoming surveys from LSST? So yeah, that's good.
Yeah, so in SDSS, the dipole is not measurable because it's just too small. So we did try with SDSS, but the signal to noise is actually below 1. And this is mainly due to the number density of galaxy, because yes, it's important to have a large volume, but what is even more important is to have a very high number density of galaxy. And so for that, SDSS is not good enough. BOSS is also just at the limit, so we cannot have a detection. It's just below. A survey which would be very good, for which we did some forecast, is DAISY, because DAISY is at low redshift and it has a very high number density of galaxy and also a very large volume. So with DAISY, we expect that we will be able to measure the dipole, to detect it, but the measurement will not be good enough for us to be able to test gravity in a very stringent way. And so if we want to do better and really to have constraint on modified gravity, then we need something like the square kilometer array. Then you mentioned LSST. LSST, the problem is that it's a photometric survey. And so we don't have a good enough precision on the redshift to target this effect, because it's the gravitational redshift. So you need to be able to measure that. So that's why we need a spectroscopic survey, which is the best part, because we
need like spectroscopic data to confirm the redshift of all the distribution of galaxies, but that's not possible photometric with LSST.
Yeah,
okay, so thank you very much.
So any more questions? I think we're good on time, and we have some great questions. So let's again say thanks to Camille.
Thank you.
And thank you everyone for coming, and hope to see you again in the next seminar. Bye everyone.
Okay, thank you very much. Bye-bye.
Bye Camille, thank you.